Hello and welcome to this video on momentum. Specifically today we're going to talk about types of collisions in reference to energy. Collisions always conserve momentum, but what happens to the energy that an object has? We classify collisions based on whether or not their energy is conserved or how much of it's conserved. An elastic collision is a collision where the energy is conserved. A perfectly elastic collision is where all the energy is conserved in the form it is. It's a fantasy, a fairy tale. It doesn't actually happen. As in any collision, there will be some transfer of energy to internal forces, such as heat or thermal energy, or between various types of kinetic. It is a theoretical construct, and while many objects will approach this, it doesn't necessarily happen. What's far more common is where we'll have an elastic collision, where the momentum and kinetic energy of the system is conserved. In other words, the kinetic energy initial will equal the kinetic energy final, and the P initial will equal the P final. Now, this doesn't necessarily mean that both objects are moving at the same velocity. There could be a transfer of velocity. It just means that the way that the one object loses the energy, the other object gains the energy, and ditto with the momentum. Some examples of elastic collisions: contactless collisions. Anytime magnets are involved, let's say the carts, or planets and objects orbiting them, kind of giving a slingshot effect. The collision between gas molecules and solid steel balls, such as in a Newton's cradle over here, aren't truly elastic collisions, hence the little asterisks here, but they're close enough that we can treat them as such. A Newton's cradle, for instance, once you start it going, it'll continue for a very long while, but there is still some small amount of energy dissipated each time. You hear it as the clacking. So these are the types of collisions where energy is conserved. Well, what about the collisions where it's not? We refer to these as inelastic collisions. Inelastic collisions are where the amount of kinetic energy changes. Momentum is still conserved. These are the majority, the vast majority of your collisions. Any explosion is an example of this because you're gaining kinetic energy. Most your collisions will be inelastic in some shape, way, or form. However, we have a step further. We can talk about a perfectly inelastic collision. Collisions where the change in kinetic energy is maximized. Almost by definition, these are when two objects stick together, such as a bullet going into a block, or two cars colliding together and sticking together. A perfectly inelastic collision is where the objects cease being two separate objects and become one combined object. An interesting consequence of this is that any collision where two objects stick together can't be elastic whatsoever. So it kind of gives you a useful shorthand. And so the idea of whether or not it's an elastic or inelastic collision ultimately comes down to calculations. Calculate the amount of momentum before, calculate the momentum after. They should be the same. Calculate the amount of kinetic energy before, kinetic energy after. Are they the same, yes or no? So let's put these terms to the use. In this collision here, this truck here is going to bounce off this red car. After the collision, the truck will be moving 10 meters per second. How fast will the car need to be going for this collision to be considered elastic? Go ahead, give it a try on your own, check back after you're done. Okay, so I started by calculating up here both the momentum and kinetic energy of the truck. The momentum of the truck would be the 60,000 Newton seconds. The kinetic energy would be 600,000 joules. So after the collision, what I need to do is I need to go through and I need to calculate how much is there. Well, there's 30,000 Newton seconds, 33,000 kilograms times 10 meters per second, and there is 150,000 joules. So the other 450,000 that had to go to the car. If I go look at the car then, 450,000 joules would equal 1 half m times v squared. I solve for v, I get 30 meters per second. And as a quick check, I can go 30 times 1,000 gives me 30,000. 30,000 from the red car plus 30,000 from the black truck means that my momentum is also conserved. Anyways, thanks for watching. Have a good one.